Welcome back, lecture 28 today, and today is the last lecture for this week where we conclude our discussion on pseudomorphic and metamorphic HEMTs. In the last lecture we talked about various aspects of pseudomorphic HEMTs for both power as well as low noise application, and we introduced the concept of indium phosphide HEMTs, which are supposedly superior to pseudomorphic HEMT in terms of low noise and high speed application, but they have lower breakdown. We discussed about the epitaxial stack. We will continue on that, and we will discuss some of the state of the art figures of indium phosphide devices for low noise application for power amplifier, and then we will talk about metamorphic HEMT. So, over to the whiteboard here, you will see that the slide that I am showing you shows you this is a very popular chart or a figure for compound semiconductor device people, both for optoelectronic as well as electronic communities. So, on the y axis you can see this band gap, on the x axis you can see the lattice spacing. You need to be having the same lattice constant to enable a lattice match. The further away you are on this, you are more lattice mismatch, which is not so good. So, for instance, gallium arsenide and aluminum arsenide have almost the same lattice constant. So, any composition of aluminum gallium arsenide is almost perfectly matched to gallium arsenide, which is great. So, L gas is always lattice matched. Now, if you recall, we talked about 50, and this is indium arsenide by the way. So, this line, okay, this line is your indium arsenide. As you keep changing the indium content from 0 to 100%, you move along this line in terms of lattice constant and band gap on both y and x axis. So, when I say 15 to 20% of indium content in GaN, so in gas, so you are probably here, somewhere here, okay, and so you are probably here. So, around 10-15% of in gas, and this will be 100% in gas, of course. So, in gas and gas is lattice mismatched by probably around 2%, for instance, in gas 15%, but that is where you are actually, okay. And as I told you, this is indium, this is aluminum indium arsenide, 48-52%, which is perfectly lattice matched to indium phosphide, which is perfectly lattice matched to indium gallium arsenide with 53% indium and 47% gallium. This is the indium phosphide HEMT architecture, which is perfectly lattice matched, okay. People also found out that on this particular platform, if you go in this direction, you can say choose an indium which is this, and that could be say 70% indium in gas. It is lattice mismatched to this indium phosphide substrate, but maybe by 2% or 3%, and that could be pseudomorphic HEMT, its lattice mismatch strain, but on indium phosphide substrate, and it will not have a problem because it is just like a pseudomorphic HEMT. You are strained, the channel is strained to indium phosphide, however the channel is indium with 70% indium content. Now, this will give you significantly higher mobility and velocity and delta EC. So, you are going to get crazy high current density GM and FT, which means you are going to get really impressively high noise figures, for instance, or high speed digital performance. So, pseudomorphic HEMTs on indium phosphide substrates are also possible. As you will see, people can move around in this, in different direction. People can move about aluminum indium arsenide, which can be the barrier. Aluminum indium arsenide could be lattice matched to 70% indium gallium arsenide, for instance, okay. This is indium gallium phosphide, this curve is indium, this is indium phosphide arsenide, for instance. Where is indium gallium phosphide? So, this is your indium phosphide, this is your gallium phosphide. So, indium gallium phosphide moves along some bizarre curve here. So, along that line you can move with indium gallium phosphide. You can have indium gallium phosphide 51% gallium, 49% indium in indium gallium phosphide is perfectly lattice matched to gallium arsenide substrate. So, you can play with all these different lattice matching, mismatching, strain, etc. to design and develop epitaxial epilayer stack to get better performance in terms of current, velocity, mobility. This is precisely heterostructure or heterojunction band engineering, and you can get significantly better performance. This ability exists only in heterojunction, okay. However, commercial success is mostly done with either L gas in gas pseudomorphic HEMT on gallium arsenide substrates or indium aluminum arsenide in gas lattice matched HEMT on indium phosphide substrates. They are relatively more commercially successful as industry vehicles for millimeter wave and even microwave, analog, very low noise and ultra high speed digital circuit applications. They are very successful, especially the military, okay, loves them because they are really high performance. This was until the advent of gallium nitride. Now, gallium nitride is going to compete with them also actually gallium nitride has largely displaced many of these technologies, especially in the microwave range, but not in the millimeter wave so much, but there is a lot of push in the millimeter wave also. Anyways, so indium phosphide HEMTs are really important for low noise. So receiver application, low noise receivers, phased array radars and high digital circuits, and so essentially this stack lattice match to indium phosphide gives you higher indium, I keep telling you, higher electron velocity, mobility, higher current density, higher carrier confinement, better GM, higher FT, Fmax and lower parasitics, because your mobility times charge density product is lower. So your parasitic also is lower because this is your sheet resistance of the 2D electron gas channel. Pseudomorphic HEMTs are also excellent for low noise, even for 100 gigahertz. Okay. The thing is, as I told you, you can make this indium phosphide also pseudomorphic, indium gallium arsenide 70%, maybe 80%, which is strained on indium phosphide substrate. You can make it with so much high content of in gas, and that will be crazy high performance, okay, which had sacrifice in breakdown voltage. Now these are some of the numbers, state of the art numbers. You can quickly go through that. I will know the thing is that the noise figure you can see for the similar frequency range going from 12 to 94 gigahertz for a indium phosphide HEMT, this noise figure, this is much better than what you saw in a normal gallium arsenide pseudomorphic HEMT. Remember, we saw some numbers from 12 to 94 gigahertz here 12 to 94 gigahertz. The typical noise figure was 0.6, 0.35, 0.9, 2.4, 1.5, 3.0, 2.1. Gain 11, 12, 10, 4, 6, 5, 3, 6. Look here, okay, here, look here. The noise figure 0.3, 0.5, 0.3, 0.4, 1.2, 0.8, 0.8, 0.7. These are in general better noise figures. Look at gain 16, 15, 17, 8, 8, 8.9, 7.6, 8.6. The gain is also overall better, the noise figure also overall better. This is in gas 70% indium, passivated device, unpassivated, etc. Okay. This offers tremendous performance improvement even over gallium arsenide pseudomorphic HEMT, but these are typically for military, as I keep telling you. Even in commercial application, the cost, it depends on cost, because this is little bit more costly because you have to engineer the epitaxial stack. So you need to put in more effort and investment in getting this done, but it gives you significant performance advantage, really low noise amplifier. For power amplifier, these had not been so attractive because of a lower breakdown voltage, but people are smart, so people have come out with techniques to improve the breakdown voltage. So to get a higher breakdown voltage for power amplifier for indium phosphide based HEMTs, lattice matched or in pseudomorphic, doesn't matter. What people do is that there are different techniques. One is the double recess you can do, the double recess is a very common technique. People can put field plate around it, which is not shown here, okay, and then the in gas cap, this cap, you can dope it lower. Of course the contact resistance might slightly increase, but you can dope that layer, you can dope this barrier lower, this barrier you can dope it lower, either the delta doping could be lower or the overall doping could be lower, so that you are slightly reducing the 2DG density, not so much but slightly, but you do not have a super highly doped cap, otherwise it will lead to higher gate leakage. So you try to prevent the gate leakage by doing these approaches. You reduce the gate leakage, you increase the Schottky barrier height on the gate stack by using different band gap material. For instance, indium aluminum arsenide or indium aluminum phosphide you can use in here, indium aluminum arsenide or indium phosphide with higher with higher aluminum content, or higher aluminum content should be higher, so that the band gap is higher. And so if the band gap is higher, then your gate Schottky barrier height phi b also will be higher, which means your gate leakage will be lower. Okay. So people can use that kind of a barrier, indium gallium phosphide, indium aluminum phosphide, indium aluminum arsenide with higher aluminum content. And then you can also use in gap channel, in gap spacer. This is the spacer, this is your spacer layer. Instead of aluminum indium arsenide, you can use indium gallium phosphide spacer, because indium gallium phosphide and in gas channel gives you a higher delta EV. In the valence band, delta EV is higher, so your whole initiated avalanche will be reduced. Your channel should not trigger whole initiated avalanche because of a lower delta EV, valence band discontinuity at the channel and the spacer interface. Okay. So essentially what happens is that this is your this thing, right. So there should not be impact ionization will begin here. The avalanche triggered by holes should be minimal. So this barrier delta EV should be large, and that is possible with indium gallium phosphide as a spacer. So those techniques can be done. Okay. And people can use composite channel. What is composite channel HEMT? I will come to that very soon. Okay. Composite channel HEMT essentially has two channel. There is one channel which is indium gallium arsenide, there is a second channel which is indium phosphide. This is a larger band gap slightly, indium phosphide, and so the breakdown, intrinsic breakdown here will be little high, and indium gallium arsenide is a lower band gap material. So, the breakdown intrinsically will be slightly low. Okay. So, you have two channel, you have, as I told you, you have one channel, you have two channel. So, this is your first channel, this is your second channel, and electrons are everywhere. Now, what happens is that when you are conducting, actually electrons are predominantly in the first channel when you have a conduction. Okay. When you are trying to conduct current in the channel, you can see that this dotted line is your electron distribution. You can see that bulk of this electron is here, a little bit of electron is here. So, you can say maybe 80% or 90% electrons will be in the first channel. Okay. That is the design, the wave functions exist in the first channel. So, lower band gap material in gas gives you excellent mobility, excellent velocity, and hence excellent delta Eg. Of course, it will give you very high current, very high GM and very high FT, great, that is what you need. What about breakdown? Now, when you talk about breakdown, you are talking about pinch off condition, like channel is turning off. So, to turn the channel off, you have to apply a negative voltage on the gate minus Vg. So, when you apply negative voltage on the gate, you are lifting this up. So, the band diagram will look something like this, correct. So, a band diagram, instead of the equilibrium band diagram this, your band diagram will look something like this. So, what happens is that you think of a single quantum well, this. When you apply a negative bias, what happens? Okay. When you apply negative bias, the channel will start depleting, right, the channel will start depleting. The electron wave function is pushed this side because you are applying a field from this side. So, electron wave function is pushed this side, which means what? Which means when you are trying to deplete the channel or you are trying to pinch up the channel at breakdown condition, your goes like that, your wave function, the wave function of electron is moved here. So, most of the electrons will exist here, whatever few electrons are there near breakdown. This material indium phosphide inherently has a higher breakdown. Okay. So, what you are doing is that your electron wave function, you are keeping it confined to the lower band gap material when you are carrying current on current. Okay. And where you are going to try to look at the breakdown or the off state, you are pushing the electron wave function into the higher wave band gap material for a higher breakdown. So, you can get a combination of higher breakdown, okay, with high cutoff frequency, high current, high GM, etc. So, you get the best of two worlds. So, this helps you get improved breakdown voltage, and this is a composite channel because there are two channels here, and this can be done on indium phosphide substrate, and that is a beautiful thing. The only problem with indium phosphide substrate in general is that the process maturity is not so much. Substrates availability 4-inch 6-inch is also difficult, and it is difficult to handle the substrates are more expensive. So, scalability, economy of scale, cost, process maturity and etc. are relatively poorer for indium phosphide than gallium arsenide. So, with gallium arsenide substrates you can scale it up, economy of scale is looking good, the process maturity is really robust. So, you can have better throughput, better device output in terms of economy and cost. That is why people prefer in gallium arsenide substrate. But indium phosphide substrate offers you significant benefit. It also enables you to have composite channel, it enables you to have best of both worlds. So, for niche application like military, space or even civilian application where cost could not be a matter, these indium phosphide devices are used. Okay. So, if I compare in general about some reported values of gallium arsenide pseudomorphic HEMT compared to indium phosphide lattice matched HEMT, this is your power density. You can see that gallium arsenide devices of course gives you higher power density as a function of frequency, of course because of higher breakdown voltage than indium phosphide lattice matched HEMT, but at millimeter wave frequencies close to 100 gigahertz the difference is not so much, because close to 100 gigahertz, if you want to get power at 100 gigahertz, your gate drain spacing cannot be too much, okay, because your cutoff frequency will suffer. Then you need to get power at 100 gigahertz, your cutoff frequency should be around 250-300 gigahertz. So, this spacing is limited. So, whether it is gallium arsenide HEMT or indium phosphide HEMT does not matter, your breakdown voltage is limited. That is why at higher frequencies your power densities are very similar. Now, here comes the interesting thing, this is power added efficiency, this is your efficiency. You can see that this is your gallium arsenide HEMT, pseudomorphic HEMT, and this is your indium phosphide HEMT. you see above around 40-50 gigahertz, this part, your power added efficiency for indium phosphide is significantly better than gallium arsenide pseudomorphic HEMT. So, for all millimeter wave applications, especially 60 gigahertz and above, for low noise application, indium phosphide is preferred over gallium arsenide pseudomorphic HEMT. For lower frequency, maybe 10-20 gigahertz, it does not matter so much, but at higher frequency it does matter, okay, even for power amplifier, not talking about low noise amplifier here. If I talk about low noise amplifier, then indium phosphide is winner hands down, okay. This is your indium phosphide gain on this side, and this is your gallium arsenide gain on this side. You can see even at lower frequencies there is a huge difference in gain. Can you see that? At higher frequencies tends to reduce, but even at 60 gigahertz you have more than 2 dB gain, that is significant for indium phosphide HEMT compares to gallium arsenide pseudomorphic HEMT, okay. It is a huge significant advantage of indium phosphide. What about noise figure? The noise figure should be as low as possible, right, because that means your signal to noise ratio at the output has not as much suffered as compared to signal to noise ratio at the input. So, the noise figure should be low. So, the low noise, this is your indium phosphide and this is your gallium arsenide and this is for this side. You can see the noise figure is significantly lower for, it is a log, dB is in log scale. So, factor of 10 you can say. Noise figure of indium phosphide being 1.2 dB when the noise figure of gallium arsenide is around 2 dB is impressive. So, both for gain and for noise, okay, indium phosphide is superior to gallium arsenide pseudomorphic HEMT, and of course, which is superior to the baseline traditional gallium arsenide HEMT for all low noise application. When I say gallium arsenide HEMT these days, it inherently means pseudomorphic HEMT only, okay, more or less, and indium phosphide HEMT means the lattice match indium phosphide HEMT, not the pseudomorphic indium phosphide HEMT, okay. That is all fine. This gives you an like a chart, a representation of what are the different frequency bands that are typically used for different application in military, commercial or civilian sectors. You can see these are radars, TV, satellite communication, etc., etc., okay. What are the devices that are typically used in the commercial sector? You can see that pseudomorphic HEMT, gallium arsenide pseudomorphic HEMT is typically used for both power amplifier as well as for low noise amplifier because of the process maturity, because of the substrate cost, because of the economy of scale, okay. However, for many things like SATCOM for instance at 44 gigahertz you do use indium phosphide HEMT, you do use indium phosphide HEMT for satellite crosslinks, okay, and especially for low noise, okay, especially for low noise avoidance radar you can use that. These are also indium phosphide, all low noise radar astronomy, radars. So, especially for low noise people use indium phosphide HEMT at a commercial scale, okay. And high speed digital communication, when you are talking about 40 Gbps, this is about 10-12 years back by the way. When you talk about really high speed digital communication, indium phosphide is used. When the requirement is not so high, 10 Gbps, people can still use gallium arsenide pseudomorphic HEMT, okay. Final section of this lecture we come to metamorphic HEMT. What is metamorphic HEMT? I already told you that indium phosphide substrate is although it enables devices with impressive performance, the substrate itself is a problem because scalability is an issue, substrate size, process maturity, substrate handling, these are issues. So, gallium arsenide substrate is preferred. So, people are smart. So, what people thought is that on a gallium arsenide substrate, can I enable an in-gas channel with higher indium content, say 40% indium, then it solves the purpose. But then the question is that if you grow such high indium content in gas, it will relax, correct, it cannot accommodate the strain to gallium arsenide. So, what did people think about? People thought that I will not grow indium gallium arsenide 40% directly on gallium arsenide because then the lattice mismatch is too much. I will grow some intermediate layers on top of gallium arsenide such that the lattice constant of those intermediate layers is not too different from that of gallium arsenide, okay. But I will gradually, as I keep growing, I will gradually keep changing the layers such that the lattice constant gradually changes to that of in-gas 40% over this thickness. You see my point? I have a starting gallium arsenide substrate, I will try to grow some layers whose lattice constant is not very different from gallium arsenide, very close, but I will gradually keep changing the lattice constant by doing something called grading. Grading means you are changing the composition of an alloy gradually, okay. Gradually you are changing the alloy composition so that the lattice constant keeps changing gradually. Okay. The lattice constant is becoming more and more gradually, and you are accommodating the strain here. You are releasing the strain in a way. This layer that you are, it is not a abrupt, it is a graded gradual layer, such that the lattice spacing is gradually changing, and at the top when you grow indium gallium arsenide with higher indium content, say 40%, the lattice constant of this material is exactly the lattice constant of the material below. So, then this channel is not strained. This is called metamorphic buffer. This transitions that you are growing is called metamorphic buffer, because you are metamorphic buffer, you are essentially allowing the strain to relax. This metamorphic buffer is strain relaxed. You are relaxing the strain, but you are also managing the dislocation. Because you are relaxing the strain gradually, your dislocations will generate, but you do this strain engineering or this dislocation engineering in such a way that you do not allow these defects and dislocations to propagate top to the in gas channel. You try to annihilate them, or you try to bend them in this metamorphic buffer, so that on the top in gas channel with higher indium content, although it is lattice overall lattice mismatch to the gas gallium arsenide substrate below, it is not lattice matched, it is not lattice mismatched to the immediate layer below. Okay, it is a gradual change and relaxing the strain, that is called metamorphic buffer and metamorphic HEMT. So, you are able to grow higher indium content in gas channel to get benefits of higher indium higher electron mobility, higher electron velocity, higher transconductance, higher current, etc., while using the gallium arsenide low cost scalable substrate. Got it? So, I told you this is whatever I have told you is written in this slide. Okay. So, metamorphic HEMTs are a very attractive and low cost alternative, because you are using gallium arsenide substrate as opposed to indium phosphide substrate, and this high indium content in gas channel, okay, and all the strain that you can have as a problem is removed by this grading layer, which is a metamorphic buffer. It is a strain relaxed buffer between the gallium arsenide substrate and the actual in gas high indium content in gas layer. You are gradually relaxing the strain and accommodating the strain. Okay. So, the high indium content in gas channel that you have grown, it will match the superior performance of indium phosphide based HEMT with the cost advantage of 6-inch gallium arsenide wafer. And that metamorphic buffer that you grow, you can also design it such that you can have indium content in the in gas channel up to 70%, not just 40-50%. That is very good, because you can have in gas 70% indium, 30% gallium, which is astoundingly high mobility and velocity on this metamorphic buffer graded layer on top of gallium arsenide. Now, this metamorphic graded layer could be some alloy of indium or gallium arsenide phosphide, etc. Okay. So, this is the schematic of the metamorphic buffer. This is your metamorphic layer that you are growing on the gallium arsenide. Typically, this is an indium aluminum arsenide buffer. So, indium aluminum arsenide, if you recall this figure, indium aluminum arsenide. So, this is your indium arsenide, this is aluminum arsenide. So, indium aluminum arsenide goes along this. So, you are going along this line, okay, and your in gas is this. So, you are trying to match this with the top line below at different compositional levels. That is what you are playing with. It is playing with the band diagram, playing with the lattice constant and band gap diagram. Okay. This is metamorphic layer, this is graded, and this is typically 100 to 200 nanometer, and you grade it from say 0 to 60% indium content. Okay. And then on top of that, you grow an undoped indium aluminum arsenide, then you grow the channel, the quantum hole, which is in gas, which is high indium content. Then again you have spacer, delta dope layer, etc., same thing. This is, and you can see that this is a gradual change in the lattice constant. You can see this is graded and a gradual change. This is your metamorphic buffer. Okay. You can see this is a transmission electron microscope that I have taken from this link below, transmission electron microscope of a metamorphic buffer. You can see these are the dislocation lines, but the dislocation lines are not allowed to propagate vertically upwards towards the channel. So, this could be your in gas channel where the 2D electron gas exists, but the dislocation should propagate this way, but they are not, they are being bent and they are propagating parallel, to the interface and they are annihilating, and so your dislocations are basically not reaching the top, and so this part is very good, you know. Otherwise, if you, and this is because of the material engineering, the way you grow, engineer the stress, growth temperature, many things, growth rate. Okay. If you do not do that well, the dislocations will propagate up like that, as you will see in gallium nitride case, and they will be detrimental to the device, but you can see that these are all propagating, they are propagating parallel to the channel, they are not propagating into the channel because of the strain engineering and the layer engineering. Okay. So, metamorphic HEMTs will allow you to have indium composition over a wide range of indium in InGaAs, and you can suitably tailor the specifications of this layer based on the requirements you need. So, metamorphic buffer can really be give you impressive performance. So, here you can see that this is your indium phosphide HEMT. Okay. This is your indium phosphide HEMT, this is a power density watt per millimeter as a function of frequency. Okay. And you can see this is your metamorphic HEMT, it is much higher than this. Okay. This is your 44% indium containing metamorphic HEMT, this is your 33% indium containing metamorphic HEMT. Still metamorphic HEMT is very good, as good or equal to or better than. In fact, this is much better, of course, the metamorphic HEMT here is much better, right. The green ones are other metamorphic HEMTs, and these are all indium phosphide. This line is basically for indium phosphide HEMT, metamorphic HEMT is much better than that. Okay. And these are some of the again noise figure, by the way, noise also can be very good, and indium phosphide HEMT is here. This is indium phosphide HEMT, this is indium phosphide HEMT. Okay. For noise figure it should be lower noise, this is frequency, you can see 100 to 150 200 gigahertz, at that frequency range the noise figure of that is of the indium phosphide HEMT. This is for gallium arsenide pseudomorphic HEMT, you can see this is quite bad compared to indium. This is your metamorphic HEMT, and you can see that metamorphic HEMT falls between gallium arsenide and indium phosphide. Okay. This is between and of course this line is predicted for metamorphic HEMT, but this data points are the metamorphic HEMTs with 100 nanometer gate length. This indium phosphide HEMTs are with 35 nanometer gate length, much shorter. So, with shorter gate length you get better noise figure. So, it is not an apple to apple comparison, these have 35 nanometer gate length, with shorter gate length your noise figure becomes better or lower. This have 100 nanometer gate length. So, inherently this has a longer gate, but even then you can see that this is much impressive than a 150 nanometer pseudomorphic HEMT technology. So, metamorphic HEMTs are really impressive, and they are also very attractive for both low noise high power application, or even low noise and even power amplifier application. But around the time when metamorphic HEMT is maturing, maybe 10-15 years back, gallium nitride HEMTs have also matured, and so gallium nitride HEMTs have entered the scene in late 90s and mid 90s to late 90s, and gallium nitride has now significantly disrupted the 3-5 semiconductor in lot of application, especially silicon LDMOS also that will come. Of course, at millimeter wave frequencies gallium arsenide is still there and it will still be there for a long time, but in the sub 6 gigahertz X band, even Q band, gallium nitride is performing tremendously better. It gives you order of magnitude higher power. You can see this is a log scale. You see the power output that you can get from gallium nitride HEMT as opposed to indium phosphide HEMT or metamorphic HEMT or gallium arsenide HEMT is at least 10 times higher in gallium nitride. It is an order of magnitude higher for the same frequency. It's really high, and that is because its breakdown voltage is significantly higher. Its current density is also significantly higher because its 2D electron gas density is significantly higher. You can see the breakdown voltage is 8 to 10 times higher than indium phosphide or silicon. So, naturally the biasing, the DC bias can be significantly higher. Not only that, for a given gate drain spacing, a given gate drain spacing will dictate your FT. For a given FT, your given gate drain spacing can block much higher voltage in gallium nitride because of the higher electric field. Okay, and that is why you can bias the device at higher voltage without compromising on the small signal FT cutoff or Fmax frequencies. So, in general, for a power versus frequency diagram, gallium nitride is looking at this upper range where you are going to deliver higher power at higher frequency. There are not many competing technologies at lower frequency, lower power or even higher power. You have a lot of competing technologies. Silicon could be LDMOS for higher power, or it could be just CMOS and RF SOI for lower power. This is something we will discuss in this course. Gallium nitride does not compete with CMOS and RF SOI, that is low power. Gallium nitride competes with LDMOS, the silicon, the big brother or the cousin of silicon, CMOS, for power RF device application. LDMOS is also used for power switching, by the way, which is not within the scope of this course, but gallium nitride competes with LDMOS. Gallium nitride competes with also silicon carbide MOSFET, but they are not so popular in RF. They are very popular. Silicon nitride JFETs are very popular in power switches, power electronics, by the way. Gallium arsenide HEMT of course is a low power, but it can go to higher frequencies. So, indium phosphide gallium arsenide will continue to reign or have the market penetration for higher frequencies millimeter wave, but gallium nitride is entering that space. Okay. So, with that we will conclude today's lecture 28. We have finished this week's lecture on pseudomorphic, metamorphic HEMTs, indium phosphide HEMTs. From the week next we will start discussing about gallium nitride HEMT, polarization, band diagram, various aspects of the device, and then we will go to what are the commercial devices that are available today for gallium nitride and for what application, and we will discuss things like the data sheet and how a commercial device is fabricated and things like that. Okay. So, I will see you next week when we talk about gallium nitride HEMT. Thank you for your time.